What's up, people? Uh, so today I want to talk about finite element method. It's a topic that I've started learning somewhat recently. I have some knowledge, and in general, I think maybe I'm better suited than most people because I have background in physics and mathematical physics and all this BS. Uh, but this particular topic, it's very challenging, and it's very hard to find any information that is not either like super introductory, where they just show some cool images with generated meshes and solutions from, I don't know, large, like developed established programs like COMSOL, ANSYS, whatever. So that's one side of the spectrum, that description is too simple, or there's like the polar opposite, where it's hardcore math and there's very little info in between. So, but I found this amazing book, so by Larson and whatever this surname is, and so they try to basically go through all the theory in very like, there's no hardcore math, but still they have some abstract ideas, in fact a lot, because this is FEM, that's how it's built. And they show practical implementations of simple algorithms. For example, of course, I've started also from the beginning, and I'm trying to learn how to solve one-dimensional problems. So if you wish to learn finite element, I think this is an amazing book to recommend. So what we will discuss today is kind of trying to build some intuition on how FEM works mathematically. Basically, I try to give my intuition how I understand a few things. And specifically, we will discuss, I will introduce topics gradually. Again, we will cover only one topic here, but I will try to introduce some ideas gradually, so the flow is acceptable, so it's easier to understand, even if like it doesn't make sense at the point when I'm saying this, explaining this. So in general, we will discuss linear interpolation, which is like the basics, few ideas, and then we will discuss topic of this lecture video, L2 projection. So it is about making approximation to functions, and in a sense, that's what FEM does. It searches for a solution that satisfies a set of equations, like many numerical models. But in like this function space, it's very abstract. So I will try to study example with vectors, which is much easier to understand. And I will try to cover a few interesting ideas from implementation, but I didn't practice, I didn't think much about this part of topic, so it might be a total mess. So yeah, let's start with what is linear interpolation. So the theory is that if we have some function f of x, and we split the domain into some intervals with using these nodes, place at x1, x2, xi, whatever, then we can approximate this function f using so-called interpolant of f. So this p is like an operator, and the idea is that we can write this interpolation of f as a linear combination of these basis functions phi, which are, in our case, they may be different, but in our simple case, these are like head functions, so they are piecewise linear. And what we should get is this kind of approximation. So in order to understand why we have this situation, why the result is that, we notice that these functions are only locally overlapping, and so it's enough, for example, to if I want to determine value somewhere in an interval between x1 and x2 or xi and xi plus 1, I only have to consider two functions in this sum. And in fact, you can see that some of these functions which are linear is another linear function. So in a sense, this linear interpolation, and if you know, of course, in order to basically linear function can be constructed from just 2 points. In this case, we get the two trivial points on the left and the right hand side because one basis function attains value of 1, another of 0, so 0 plus 1. Yeah, just had a small brain freeze. The important thing here is that coefficients are sampled from this function at this particular node. This xi is a node. Yeah, and what we get is just simply a line through these 2 points. And this is the idea. Here, these head functions are scaled by function value at these points, and we get this particular interpolant. We will discuss few ideas now, which are also kind of will be important or help you to build intuition. So this may not how you think about projections, but yeah, let's go with it. So assuming we have a vector that's built as a linear combination of basis vectors in this way, so our expression for interpolant of f looks exactly like a linear combination of some basis vectors with some coefficients xi. Okay, and so there's like they are very similar, and in fact in linear algebra, I'm not sure it's considered linear algebra at this point, but still, yeah. So some object is expressed as a linear combination of some fundamental blocks. There's some sort of relation. And the interesting part is that components of this vector, v1, vx, vy, whatever you call them, they specify some point in some space, Rn. So usually we interpret it geometrically. So it's just a line or an arrow or segment from our origin to this point. But when we talk about this linear combination of function, in this particular case, it becomes very interesting because we can also consider these basis functions as typical basis vectors, and all the points, all these kind of coefficients xi. If you move through this space of these coefficients, basically what you get is you get different piecewise linear functions. So you can basically, by searching in that function space, you can reconstruct arbitrary functions. Of course, you can like make intervals smaller and smaller, and you can approximate better and better. It's a very nice idea. Now, with linear interpolation, there's a bit of a problem. If this interval is huge and the function changes too much, so is this the best approximation to this function? For example, if we consider here this case in blue shaded kind of region, it is an error. So area is kind of related to how good approximation is. We want to lower this. And so the question, does linear interpolation, is it the best? And basically I can offer you another version of another linear approximation, which will produce much lower error. So in a sense, we can think that because it's a function, that the error is an area. Okay, we just have to integrate something. So in this case, we, like, for example, integrate the absolute value of difference between these functions. So this is important idea. And the third is kind of, this one was about projections. Maybe you don't usually do it, but yeah, again, consider that you have a vector that is linear combination. And then if you want to extract the, for example, vy component, you have to, I mean, you can mathematically just try to use a dot product with y basis, and you see, due to orthogonality and orthonormality, the multiplication with ex will be orthogonal, give 0, this will give 1, and you will get your vy component. So this is the dot product. We can refer to it as an inner product. You will see later. You can think about it in geometrical terms, because we know that if we have this situation, this right angle triangle with v magnitude as hypotenuse, and we know that cosine is expressed as such, basically we get the same expression. So we can think about this as geometric projection. So yeah, it's just one idea. These few important ideas, I'm not sure they will be very relevant, but it's important to keep track of them. So now we will talk about L2 projection. And basically, we know that, for example, we can have a problem, a matrix equation mx equals b, where M is a tall skinny matrix, times some vector equals vector, right? We know that in general there will be no solution. You can think about it differently, just purely like mechanically. You can say, okay, you have to have a determinant of non-zero or something to have a unique solution. But again, we can return to my best approach is thinking of these problems as linear combination of finding such linear combination of vectors, column vectors in matrix M that will point to the vector B, like this. Here is kind of, okay. Anyway, you get the point. And now the question about whether there will be solution or will not be solution, it boils down to whether these two kind of new basis vectors, whether they can reach this B vector. And so for example, in this tall skinny matrix case, we will have situation where, in a sense, B can live in R3, so three-dimensional space, but we only have two columns. So any linear combination of these columns will only span a plane. Unless we're very lucky and B lives on that plane, we will not find a solution. So the situation will be like this: two vectors that lie on a plane, and our B, which is here V3, is out of the plane. And that's it. We don't have solutions, we give up. Or we can think, okay, we can try different linear combinations, so trying different x and y combinations, and build such solution that will minimize this kind of error. So this error is a kind of vector that points from our proposed solution to the final solution. And of course, the idea is that if we want to minimize, like, we want to make it as close as possible. So we want to minimize this error. And of course, like, for this particular problem, we can say, okay, it should be a projection, but I want to explore a little bit deeper, maybe build some additional intuition. So clearly we want to minimize this error. And again, let's discuss why it's called L2 projection. So in a sense, let's consider that we don't know exactly this solution, the best projection. This can be either two-dimensional problem or kind of a view from the side of this. So in a sense, we pick some test vector, test solution vs. We construct this error, and it kind of creates this right angle triangle. And of course, what we want to do is reduce the hypotenuse. So in fact, we know that we can modify this vs because we can construct any vectors on that plane. And so we just want to reduce this side, which I call delta, to 0. And of course, by Pythagorean distances, it will minimize the hypotenuse. So what we observe is that our solution will become orthogonal. Okay, geometrically it will be orthogonal to our test solution. And maybe we can expand it a bit more. We write that this test solution is a linear combination of our basis vectors, columns of this matrix. And because generally this V can be anywhere, that means X and Y, these coefficients, should not be 0. It's only possible when basically projections of error onto our basis vectors are all 0. You might think of it something like these basis vectors produce such coefficients that error has 0 projection onto them, something like this. I don't know. In general, we come to this expression. It's basically our solution if it's proper, if it's best in that L2 sense, it will behave like this. Maybe we can rewrite it. We know this error. It's a target minus our solution. In fact, what it is our solution is just projection of our target onto our basically plane. And it will be true for any basis vectors. We can, by the way, check this mathematically, whether this works. So I have recreated in Python this particular problem. What we expect, usually what we do in order to calculate X, we calculate M inverse and multiply by B. But now notice that we cannot even get an M inverse because this is not a rectangular matrix. So instead we can do pseudo inverse, and what it does, it actually does this minimization just mechanically. And then we get our V solution by multiplying. In perfect scenario, we will expect it to be B, to reconstruct onto B. But in fact, they are not equal, and so we have some kind of error. So interestingly enough, I've checked M inverse multiplied by M, which should give unity. In fact, it gives here unity. It's I'm a bit amazed. But usually it will be something like something diagonal, about diagonalish as possible. So yeah, these are coefficients for our basis vectors. This is solution. We'll see it lives in xy plane. And we see the error is pointing straight up, so it's orthogonal to this plane. Okay, now we'll move to actually function stuff. So we will, instead of our vectors v1, v2, we will have v hat. So it's kind of a space that is spanned by these vectors phi1, phi2, and so on. Now about inner products and projections, So for functions, because they are not simply numbers, we actually have to have some kind of operator that integrates, that reduces them to some number. In fact, it's defined as generalized inner product as this. So function can be kind of orthogonal or something similar on a specific region interval, right? And here it's complex conjugate, but we will use real numbers, so you can kind of ignore it. And so in the book, the definition of L2 projection is the following. So it if I would see it for the first time, I wouldn't understand anything like completely. So here they use pH as this kind of projection operator onto hat basis. So this expression looks like this. We can rewrite it using our inner product as follows. So F minus projection of F dotted with some basis vector V. This is basis function, and we can compare it with our result from minimization problem, and it is pretty much the same. It's absolutely the same idea. And so even the images, right, they're absolutely the same. That's what I tried to recreate, except in this case we have VH, some kind of plane space spanned by hat vectors or something. So it would be really confusing. And the interesting part, again, because this is integral and basically we are dealing with functions, it is also an approximation. We can produce an approximation. So in fact, we see that a result of this particular L2 projection gives you not linear interpolation, but something a bit different. So in fact, these nodes, they are not lying on a function. And of course, using this definition, we know that our projection into hat space should be a linear combination of hat functions. And that's what we do. Write it as these xi are unknowns. We rewrite it into like n different equations, and it should describe basically matrix equation like this xi m equals b. These xi are unknowns, and that means you can solve for xi that minimize this L2 kind of minimize, and it's trying to recreate this function, blue function. And then you take this xi, input into your ansatz basically, and it should give something that is similar. Now this part is kind of experimental implementation. It's kind of dry, but I found some interesting ideas and how challenges were solved. So right, that's what we said previously. That we have these coefficients, we can construct these matrix equations. Remind you what our hat functions are. That they are 0 at neighboring nodes. They are 1 at node that is at center. And that's it. And so we have to actually calculate, this is called a mass matrix for historical reasons, maybe because FEM was developed in using for solid mechanics. So that's where its roots are, and B is a load matrix. So yeah, we see that in order to actually construct linear equation, matrix equation, we have to construct these matrices with these terms. So we have to actually integrate our hat functions. And this is what we'll try to do. If you approach it kind of naively, it means that you understand how to integrate. it might be a bit painful, because in a sense, let's consider diagonal element mii. So it's a fi function multiplied, basically squared, integrated on this integral where it's basically non-zero. And it will be either, also it is piecewise function, but it will kind of piecewise linear, and so it will be piecewise quadratic. So you say, okay, I have to split it into two segments and then calculate the areas. And you start to think, okay, first I have to express, write actually these linear functions, and that means it will be some kind of slope times x plus offset. And you're starting, okay, I know the slope. Here function reaches 1, and here is a distance h, which we define as follows. Then you try to go on and go on, and then you try to take a square, and okay, what will you do? I mean, it's doable. It's just, it will be a bit painful. And what will you do for entries that are not diagonal? Although not diagonal entries also will be all zero except the ones that are close. The distance in indices is not greater than 1. Maybe we can kind of exploit some symmetries, because these are areas. So, okay, let's say maybe we can translate it. This is kind of useful, by the way. Especially if some functions will be like 0 at endpoints or something. We can translate functions, which is I'm trying to show you here. So this will be equivalent is integrating from 0 to width. And even maybe we can reflect them, because area is conserved. Not conserved, but area is area. Area is like scalar. Okay, and what can we do to avoid all this math? And so book offers to use so-called Simpson's rule, and it's derived. Okay, if you go to Wikipedia and we'll try to find how it's derived, it will be mad. Like derivation for Simpson's rule, you have to construct Lagrangian polynomial bases. Actually, I've done it, but yeah, it's much more difficult than you can see in example from the book. So what they do in a book, they say, okay, we will try to explain it this way. First of all, we're trying to interpolate our region, one piece of our head function as quadratic equation, and then we notice we can obtain these coefficients C1, C2, C3 from these boundary conditions, kind of boundary, so value on the edges and value in a midpoint, and then we can construct this matrix, and all what we have to do is solve for coefficients. But that's only an interpolation approximation, right? Although this will be kind of constants. So in fact, we have to also integrate this in approximation. And what we get is this expression, Simpson 1/3 rule, although here you have 1/6, but I think he used basically not midpoint, but either a plus half distance or something, so it reduces to 1/3 here. So b minus a is equal to half distances like this. 2 divided by 6 is 1/3. Anyway, so we can approximate this integral, or the definite integral, using this approximation, using this formula. And so we see what we can conclude, that in order to calculate this particular integral, we need just interval width and function values at left point, midpoint, and right point. Fortunately for us, a left midpoint is 0. Here, left midpoint is 0. Right midpoint, again, we are talking about this particular case, subcase, one left hand side. Right hand side is 1. Now the question is, what about the midpoint? Okay, we still have to calculate something. But no, actually, you can notice this. If, for example, if we take as a reference example this squared function x squared that attains 1 at argument 1, and then we like scale it to some distance h, I don't know how to express it, we see that also the midpoint, it also is stretched, so it kind of it retains the same value as what function would retain if it was like simple not scaled version. It's just visual observation. So maybe I'll also try to express it mathematically. Kind of let's do it briefly, but okay, we have a scaled version by h of our function. It is divided because in order to reach 1 here, we actually have to reach x equal to h. But on the other hand, we need a coordinate transform, which acts in the opposite direction. I guess to keep everything equal in different coordinate frames or something. I'm not even sure that it works correctly, or I'm just cherry picking. So yeah, if our axis also scales, we see that our scaled version evaluated at its midpoint will obtain the same value as not scaled function. It may be obvious, but yeah, what we can deduct is that our integral is not even dependent on this interval width. So in fact, in the midpoint, it will attain always 1/4 independent of how wide is the interval. And okay, our integral reduces to this particular interval width and 3 numbers. And our Simpson's formula reduces to just h interval width divided by 3. Okay, we have to consider also the other part. You can either try to think about reflections or just swap the a and b, and you will get the same expression, except the right interval may be of different width. That means that each diagonal element of this matrix will be just sum of basically widths of neighboring segments. Now the question is, what do we do about these non-diagonal entries? So phi I times phi j. It looks like this. We see that we have to integrate whole distance, but one function becomes 0 here and 0 here. So effectively we are only interested in this segment interval. And here also, just by observing, we can solve it very, very easily. So again, this will be our integral, and we have to collect interval width, left-hand side value, Oh, I understand. So the left-hand side interval will be just this function times this function, so 1 by 0. In the midpoint, they will attain so yeah, one half from one function, one half from another function, so 1/4. And again, on the right hand side, one of the functions will be 0 and one other is 1. And so interestingly enough, here also this integral becomes very, very simple. Simply this interval width divided by 6. So we have obtained this mass matrix entries of diagonal. There are some observations interesting that you can split it into multiplication of n matrices and our number of intervals or nodes, I don't remember. So they explain how you can construct it easier, build with each evaluation of interval. Now the problem, kind of, we have constructed M, but now we have to construct B, load vector. And in fact, we cannot do as simple as here, because this f function, it actually will be across our head function. It will change. So instead, we actually have to somehow integrate. And in book they propose to use trapezoidal rule also, but we also can simplify things, because we know that on the edges we will have something multiplied by 0, and we will get some values of this vector. So in a sense, we return to this idea that we got. We can construct this particular matrix equation. Now we have entries from M and for B, and we can solve by inverting coefficients for this approximation, for L2 approximation. And that's pretty much it. I think this last part was particularly interesting, because if you were to try to solve it just by conventional integration, it will be much harder than to use Simpson's formula, Simpson's rule. And so I want to show you, I've implemented it in Godot. I was just playing around with this engine, and so as a test case, I've decided to implement it. So few differences. My y dimension is flipped because of how they treat coordinate system. They are more akin of matrix notation. So we see the same situation. Here I can control number of elements. You can hardly see here, but you can see the basis functions, and you can increase the number of them, and it will recalculate this. It will reconstruct this matrix equation. It will grow, of course, because I have more intervals, finite elements, and that's what you can observe. It approximates better and better. So it's kind of nice. I will do something more later. Now, why I wanted to talk about this particular L2 problem, because it involves this type of expression. Basically, some function times another function, and it's a part of I think like variational analysis. I guess it's closely related, and you see it in a FEM textbooks a lot. So although this particular expression will not be used, it I think is used for evaluating errors, but later we will see, if I will get to it, that you have similar expressions for actually formulating problems mathematically. In fact, you see here some kind of f multiplied by, basically that's what you see. There are test functions, trial functions, whatever. So it's kind of closely related. And this particular formulation, because we formulate it in terms of integral, is why it's called weak formulation. But yeah, we will get to it later, at least when I will feel like I understand it nicely. So yeah, that will be end of this particular lecture. So we discussed linear interpolation. So it's very simple, but it doesn't involve any like, it's very like heuristical, or it's just very like mechanical. It doesn't have any beauty, any kind of minimization. So these ideas that I tried to introduce, actually, that if we are dealing with functions, we could possibly minimize error by basically integrating something, just to remind you of what projections are, and then that dot products can be viewed as projection. And then I've introduced this problem of matrix equation, matrix problem that has no solution, but it can be solved. But you can find solution that is close enough in this L2 way of thinking. So minimizing this kind of hypotenuse, minimizing the error. And that it can be, basically, it completely mirrors what we see in this formulation of interpolation, basically, of finding coefficients for interpolation. And implementation, you know, it has few interesting ideas. That's only why I wanted to show you and share with you these ideas. You can read up on Simpson's rule and Lagrange polynomials. It's a total mess, but it's fun. And in general, like, I think you should know about approximation using polynomials, and that there exist like different bases, basically. Legendre, I don't know, like some kind of different type of polynomial bases, and they all, although they all produce some kind of polynomial with some coefficients, these coefficients will be different for different bases. And so some bases may behave way better than other bases. I think that's important to know, because polynomials have very bad reputations for people because we are generally not taught how to approximate stuff. And so knowing this, at least, I think will help you. Yeah, Simpson's rule. I think it's cool. I think it's cool that you have to only get 3 points in some scenarios. Like here, the midpoint was very easy to find values, and the side values also. It completely trivialized original problem where I would have to integrate square of some function, even if it's polynomial. I mean, it's not tragic, but compared to this, it's nothing. So yeah, then we discuss how to fill this mass matrix, diagonal and off-diagonal components. We don't have another components because functions stop overlapping. And for B, for load vector, I didn't go into it, but basically we can only approximate. So we cannot use these cool tricks. Maybe we can. That's what they do in a book. Yeah. And then we see my interesting study case. So yeah, that will be it. Thanks. See you in next video.